Okay, so I think this is a new feature in Zoom that it actually tells me that recording has started. And believe me, the last few times I jumped violently, wondering who was talking to me. But at least today I didn't do that. Okay, so I'm kind of getting used to it. We are not like you guys. You guys, like, you grow with software. Yeah, changes and all are something that you can handle very easily. I'm somebody who doesn't like change. Okay, so when a new feature comes in, you have me floored. Anyway, so let's go on to the one dimensional simple harmonic oscillator. So let me just write it down. Of course, in this context, I will also solve a few things about the three-dimensional harmonic oscillator. Actually, not few, maybe just one problem or something, but it can be done pretty easily. All right. So one-dimensional linear harmonic oscillator. Yeah. So what are the things that you need to kind of really know about this? Okay, just one second. Let me admit some two people who have entered the, yeah, it was poor Tanya, I think, who kind of got boosted. Okay. So, what is, first of all, of course, you should remember how to write the Hamiltonian, right? So, the Hamiltonian, of course, has essentially a kinetic energy part. And since this is a one dimensional harmonic oscillator, we can merrily write it just like this. And then you have the potential energy part, which is in quantum mechanics, we tend to write it like this. Okay, if you remember, of course, your potential energy is usually written as half kx square, but then your k is root of, sorry, not k is root of, usually you will write it as omega is root of k by m. All right, so thereby the what do you call the equivalence? All right, just one second, let me see. Okay, I think she's having some trouble, poor thing. Yeah. So now, this being the Hamiltonian, let's go on to the Schrodinger equation. It's a time independent potential. So, of course, you're going to write down the time independent Schrodinger equation, which is essentially an eigenvalue equation for the Hamiltonian. So, the Schrodinger equation you write, you will essentially say that minus h cross square by 2m d square by dx square plus half m omega square x square. This whole thing acting upon the psi of x will give you e psi of x, right? So this is essentially how it looks. Now here, of course, you bring in, just one second. All right. I think it's poor Tanya. She's having some trouble coming in. All right. So here, yeah. So what do we do with the? We introduce these two operators. So they are, known as the ladder operators, the creation or annihilation operators. Okay. So they have different names. So essentially, you can go as a plus or a minus. Please note that sometimes they are written as a and a dagger. Okay. So the a dagger is usually, I think, a plus. All right, and this is a minus. So kindly do not get confused in certain places if they have written it in terms of a and a dagger. You do know that this a plus and a minus are essentially the um, adjoints of each other, right? Yeah, they are adjoints of each other, right? So essentially, one is the a dagger of counterpart of the other. All right. So thereby, you can write it also in this particular what do you call it? Uh, Format that I have written over here. Instead of using a minus and a plus, you use a and a dagger. All right. So now your a plus and a minus, I'm writing it in a slightly different form from what I showed you last time, because maybe I think this may help you remember it better. Okay, I have a problem. You guys may not, with remembering, certain formulae, but this is essentially how it looks. Okay, so there is this constant outside, and then you have, so this over here, if you look at the a, I've written plus on top, minus at the bottom. Here you'll write minus plus I, and then this is your p operator. Okay, plus m omega x. Okay, so this is how you can try and remember your A plus and your A minus. All right. Now, in terms of the A plus and A minus, of course, your Hamiltonian, okay, and I would suggest that you try and remember this. Your it becomes H cross omega, A minus A plus, okay, minus half. All right. Or you can also write it as equal to H cross omega, A plus A minus plus half. Okay, so this is, again, if you can kind of remember this, it will help you. Right now, of course, what is very, very key is the commutator relation between A minus and A plus, and you all know it is essentially 1. Correct. Now, let us move on to the uh, what is exactly the action of A plus and A minus, and this is a little important for us to remember. So, if we can write the Hamiltonian acting upon, so I can, yeah, let me just go ahead and just do this. Okay, we get an En psi n, right? And what you do know is that, so if this is the case, then your H acting on A plus psi n, okay, what will it give you? It will give you essentially En plus H cross omega, and then you will get A plus sign. Okay, so this is kind of important to remember, that your A plus sign is also an eigen function of the Hamiltonian, and it has an energy which is raised by plus H cross omega. So sometimes A plus and A minus are also called the raising and lowering operators, ladder operators, raising, lowering operators, also creation and annihilation operators. Okay, so what about H A minus psi n? This we have to be a little careful. Okay, so if this will become En minus H cross omega A minus psi n. Okay, provided that psi n is not equal to psi 0. Okay, and what is psi 0? Psi 0, of course, is your ground state. And basically, you have the situation of H psi 0 gives you essentially E0 psi 0. Okay, so what is the situation if you do an A minus operation on psi 0? Please remember, this will give you a null vector. All right, so this is your null vector. All right, so please remember that is the situation. Now, what are really the values of these E0 and so on and so forth? All of you know, I think, no, I mean, definitely, is this is nothing but H cross omega by 2, right? And then your En is nothing but N plus half, I would say, H cross omega, where N is 0, 1, 2. So please note here, n does take on the value of 0. Okay, which was not the case when you were doing the infinitely deep square well. All right, so this is one thing that you have to realize. There the allowed values are 1, 2, 3, and so on and so forth. Here the allowed values are 0, 1, 2, 3. So it is, that is basically what you call as counting numbers, right? Yeah, and here these are whole numbers. Okay, so I natural numbers, I think, is what it was called when we were in school. Okay, and these are nothing but whole numbers. Right now, how would you define the psi state? Okay, you would be able to do it, okay, as an A plus acting n times on psi 0. And what is an? Of course, is your normalization constant. In a bit, I will just tell you what the form of this wave function is. All right. Apart from this, what do we need to remember? Yeah, the action on A of A plus. Okay. So A plus acting on psi n, what will it give you? It will be essentially giving you n plus 1 to the power of half, and then you will get psi n plus 1. So this I would request you to try and commit to memory. Okay, this is very important, and it's a little important that you have it committed to memory. What else? Okay, your a minus acting on psi n will actually give you n to the power of half. Okay, and here you will get psi n minus 1. Again, exception being this. Okay, it will actually come out to be 0 because you will do a, I mean, you will not be able to do a n minus half. Okay, and then your n to the power of half will be n will be 0, so it will work out. But the point is that you should remember that you really cannot lower. Okay. Oh, this poor girl is really having trouble today. I hope she's able to join us. Tanya, I hope you are with us, okay? So, yeah. Now, what else do we need to know? That when you actually do a psi n, this is nothing but, okay. Yeah, so I will just do it over here itself. I will not put it separately over here. This an actually works out to be 1 by the root of n factorial. If you can commit it to memory, it will be good, but don't worry too much about it. Okay. Usually exams are not really such that you have it's not your memory being tested for most of the time. All right. To an extent, yes, but not very hugely. Okay, so now one thing that we can, yeah, this is a very important relation that you have to remember, is how to write x and p in terms of a plus and a minus. And if you, this is nothing but h cross by 2m omega, the entire thing under root, and this will be a plus a minus, if I'm not mistaken. Yeah, a plus a minus. Okay, and your p on the other hand is essentially I, and then you have h cross m omega by 2, and this is essentially a plus minus a minus. Okay, so these two, the last two formulae, are fairly, they are required. All right, so let us now move on. What else do we know? So I will just give you now the full form of the wave function, and then we will just go through a few problems which you may have done. I would think that you would have done in your first semester. They're kind of important. Let us just try and look at those things. I have them worked out already, so I'm hoping those scan sheets won't be difficult. I will send them across to you. All right, so in case you need a quick revision, you can just look through those. If I made any mistakes, kindly forgive me. So because as I say, most of the time these notes I wrote for myself. Okay, it wasn't really meant for any kind of public consumption. All right, so if there are mistakes, kindly do not hammer me for it, but yeah, just let me know so that I can actually rectify it, and your juniors will not have to suffer the same fate as you. Okay, so let me just write down the form of the wave function. All right, so the wave function, your psi n x, okay, in all its glory, all right, ugly glory, let me say. Okay, so you have essentially m omega by pi h cross, and this actually goes to the power of 1 by 4. All right, and then you have 1 upon root of 2 to the power of n factorial. Okay, and then you have essentially a Hermite polynomial, all right, of the nth order, and this is the parameter we use, and this is this e to the power of minus square by 2. And what is this guy? This guy is nothing but a proportionality with x. Okay, so what is that proportionality constant? It is m omega by h cross and then into x. Okay, root of m omega by h cross, sorry, into x. Okay, so this is essentially the what do you call it? The wave function. Okay, 1 second. Let me admit another person. Yeah, this is the wave function. Now, yeah, so what the Hermite polynomials, your H naught is equal to 1, your H1 is equal to 2 psi, and your H2 is equal to 4 psi square minus 2. Okay, now and so on and so forth. I'm not going to write down more Hermite polynomials. It would be good if you can remember the ground state. What is key that you remember that it is a Gaussian. Okay, looks like Gaussian, right? Okay, so now what we will do is I will just go, because I'll have to draw these figures. It does take me time and I don't do a very good job of it. So I'm going to stop the share with this particular thing, and I'm going to share hopefully my handwritten notes, which I don't see. Done. Okay, just 1 second, guys. I don't know how to handle this situation. Okay. Yeah. There you are. Not this. Yeah. Okay. Let me see now whether it appears on my share screen. Yep, it does. All right. Share. Right. Okay. So this is essentially the whole lot of things that I told you about. Oh, I'm not sure if this is too visible to you all. Is it visible, please? This particular thing that I drawn? If it is not, then I will just draw it for you. Is it visible?
Yes, ma'am.
Huh? You can see it. Fine. So what you can
But
see,
somewhat erased in between.
sorry, yeah, it looks bad, no? Okay, I'll do it. I'll just draw it. Yeah, it's okay. I mean, I was basically trying to. So I'll stop that share. I'll share again with the iScribe. Yeah, I'll just draw it again. Okay, so basically what is our situation? So we have over here our center of the well, right? And this is of course our x-axis, right? And the harmonic oscillator is supposed to be centered at 0. All right, x is equal to 0. And then you have of course your potential, which is a parabolic potential, right? Yeah, so this is like a half kx square. All right, it's not coincided very well. That's the reason why. So now the point is that your energy levels. Okay, so let's imagine that this is an kind of an energy axis. Okay, so I should be able to plot both the potential energy and as well as the energy states, the total energy on it. Okay. So that's why your dark line is essentially your potential energy. All right. So then this is essentially going to be at half h cross omega, right? Yeah, this first line. And then let's do this. This is going to be your first excited state, okay, which is going to be at 3 by 2 h cross omega. And then, of course, you have your next excited state, which is at 5 by 2 h cross omega, right? And then, so remember that the first step of the ground state, okay, because there's nothing below that. All right, again the weirdness of quantum systems. All right, so it's not 0, it is essentially half h cross omega, and then you keep having essentially evenly stepped, even steps, okay, for the next excited state. All right, so the separation between all the states is h cross omega. That's your step size. Now, what is the wave function? So I'm just going to draw the wave function over here. So this first one will look like this. Okay, so this is your first one. Then the second one is essentially, it goes like that. All right. Your third one is something like this. Okay. And your fourth one is something like, I think it goes like that. Okay, I hope I've drawn it correctly. So there is a symmetry, of course. All right, the fourth one doesn't look very symmetric. I'm very sorry about that. Okay, what is more, like should be more important for us is what is the probability distribution. Okay, and I think this you should really keep in your heads. Okay, so again, let me draw your. Uh, okay, I think I went a bit bonkers at the end. All right. But yeah, at least the minimum I think has kind of coincided. So then again, let me draw your states. Okay. So, one thing which I request you all to do is please draw the plots yourself. Okay. This may not be too important for you in, like, I mean, very often in the exams in the university, your people draw plots and, very rarely, let me say people are not punished for drawing bad plots. Okay. However, it can be critical in an interview situation. All right. So please, okay. Multiple choice questions also, it may not matter. But you go to a critical, to an interview and you've been asked to draw a plot on the board or on some kind of a software. All right. You muck it up. All right. It leaves a horrible impression. Okay. A very, very bad impression. So I would suggest that you take your pen, pencil, learn to draw good plots. All right. Don't look at ma'am. Ma'am is probably mucking it up, but the feature should be correct. Okay. So this is how your probability distribution position. I mean the where you can find the particle. Okay. That essentially looks like this, right? For the ground state. Now, what about this? This will have essentially two humps. All right. Both of equal height. This guy will have actually three humps, but the center guy actually starts going a bit down. All right. Then this guy is even more lopsided. Okay. So it will be, all right. So these two will come down. So what I want you to note, okay, is the fact that they are fair, it's completely symmetric about the equilibrium position. All right. You look at the zero state, the two state. Okay. There is actually a probability, there is a finite probability of being present at the x is equal to 0, which vanishes for the odd states. Okay. It's important that you kind of notice this feature because there are certain problems which may require this particular knowledge. All right. So please note that in the case of the third excited state here, okay, this one, right, you can see that the probability of finding it at the equilibrium position exactly is 0. All right. Similarly here. Okay. So 1 and 3, n is equal to 1 and 3, it has vanished. Okay. Whereas it is finite for the case of n is equal to 0 and 2, and thereby for 4, 6, and so on and so forth. Okay. So qualitatively, you should be able to tell the difference. The other thing what you have to notice is that you look at the situation in the ground state. Okay. The probability, maximum probability of finding the particle is at x is equal to 0. Yeah, because that's where it peaks and then it dies off. Correct. Now as you go to extremely high states, what do you kind of expect? Okay, so let me just draw how the probability distribution would look for very high n. All right. So for very high n, essentially, so it will be of course very, very symmetric. All right. And you will have maximum probability at the, so you will essentially get into a situation which will look like, okay, I didn't manage to reach that guy, doesn't matter, but the profile which I want you to see is essentially a dip to a minimum and then an increase again. Okay, so this is essentially your P of X. So let me write over here, this is your P of X. Okay, and this is your X, and this of course is your 0. Okay, now what you have to realize, this is for very high N. Okay, and if you think about how the situation will be for your classical harmonic oscillator, okay, so can anybody just tell me what do you expect to be the probability distribution for a classical oscillator? Where will it be maximum? Where will it be minimum? Any thoughts?
Probability, ma'am.
Sorry?
Like, can you repeat the question? Did you ask
Yeah.
about what is
What
the
I'm asking is
probability?
that the probability of finding the system, all right, at as a function of position, right? This is what this is, right? Isn't it? It's a probability of finding the particle, or this for that matter. Yeah. Probability of finding the system as a function of the position, correct? So the position probability distribution in some sense. So I'm asking you that for a classical oscillator, what do you expect it to be?
At extremes, it has to be high. No?
Yeah. Why do you say that, Medha? You are absolutely correct. Why do you?
Potential energy is maximum there. So,
Is that really? Would that make sense? I mean, like, why potential energy being maximum would mean that the system spends more time there. Is
Even
it
if
um,
we
more,
if we
simple way of putting it?
it's position dependent. No?
Of course, it's position dependent. That's what you just said, right? It is position dependent, but you're saying the probability is going to be highest where the potential energy is the maximum. Why would you say that? Is what I'm asking.
Um,
Okay, let me give you guys a clue. Okay, so you're right, Medha, in some sense. Okay, you're completely right, but let me give you a clue. All right, you would say that the probability is going to be maximum when the particle spends most time there. Is that okay? Everybody agrees with this?
yes, ma'am.
Huh? So now the thing is that time spent in a position, would you agree it will go inversely as its velocity? If it has a high velocity, it will spend less time. If it has very slow velocity, low velocities, it will spend maximum time. So will
Uh,
you agree with that?
yes, ma'am.
Right. Now tell me how the velocity changes.
It is maximum at the equilibrium, whereas it is
Absolutely.
minimum at the extremes.
Absolutely. Okay. So that is the reason why in a classical system, we expect the probability to be highest at the extremum positions, okay, at the amplitude, the minus a and the plus a, right? Yeah, we put that as the, so there we know the velocity goes to 0. Those are the turning points, correct? Yeah, so we expect the velocity to go to 0. So there the particle or the system, you could say, spends maximum time. So if you were actually trying to look for the oscillating particle, chances are that you will be able to find it at the extremum positions because it spends maximum time there. All right, whereas at the equilibrium position, what is happening, it is essentially just scooting past because its velocity is the highest, correct? So what you have to realize is, for a quantum mechanical harmonic oscillator, look at this ground state. Okay, you see that the probability is maximum at the equilibrium position. All right, it's completely inverted compared to what you expect for a classical oscillator. However, if you go higher and higher in n, then you end up with a probability, position probability distribution like this, which is approaching the classical uh, distribution. Okay, so this is a very very important thing, just wrap your heads around it, simply because I think people just throw, it's first of all an extremely interesting thing, and the second thing is that it is something that people just throw in various forms, questions based on this. Okay, so the best argument that you have for the probability distribution of a classical harmonic oscillator is think in terms of the velocity. Okay, where does it spend minimum time, where does it spend maximum time, and voila, you have it. Okay, not just for the harmonic oscillator, any system. All right. Okay. Right. So what we will do now is we will go ahead and look at a few problems which I do believe that we did might have done together in class. Okay, but nonetheless. Okay, so I'm going to stop the share and I'm trying to go back to my notes. Okay, and I'm hoping that, yeah, even if the diagram was not clear, maybe those things will be a bit clear. Right, so let's just move down a bit. Okay, so yeah, it does look a bit erased. And what over here, if you remember, when we did things using formalism, okay, we really didn't get the form of the wave function. Okay, and I said that it was a little immaterial. You could still work with a notional wave function and just, manage the whole scenario. All right. But I may have done this in class, doesn't matter, which is why I have my notes out here. Okay, so that we can run through this quickly and I will not bore you guys. Okay, so what do you so just look at the problem over here. It says solve for the ground state of the harmonic oscillator using operator formalism. Okay, so you're supposed to go with operator formalism, not write down the Schrodinger equation, and try and get the ground state solution. All right. So what, and then of course it has asked you also for the first excited state. So here you start off with this. Okay, we all know this particular thing, that A minus acting on psi 0 gives us a null vector, right? And we know how to write down the A minus in terms of the P and the X. So I have used exactly what I have written over here, that 1 upon root of 2 h cross m omega. Just 1 second. Yeah. So you have, one has written down exactly this form, all right? And this acting on psi 0 gives us a 0. And then, of course, go ahead and put in minus IH cross d by dx for P, all right? And then what you have is essentially a differential equation, okay? You have a differential equation. Your variable, of course, is x, okay? And you have to solve for this psi 0. So you will get essentially this constant 1 upon root of 2 h cross m omega. And then you have over here this I, and this minus I, of course, just gives you a plus 1. So you have an h cross d by dx plus m omega x acting on psi 0 gives you a 0. So you can just go ahead. This is a very, very simple differential equation, something that even SB ma'am can solve. Okay, and you end up with this as your solution. Okay, so your ground state, okay, psi 0 x is equal to a e to the power of minus m omega by 2h cross into x square. Okay, so this is basically your ground state wave function. A, of course, you can just get from your normalization. Okay, so if you normalize it, you will end up getting this particular value. All right, so m omega by pi h cross to the power of 1 by 4. All right, e to the power of minus m omega by 2h cross x square. So, it's a very, very easy way to get to the ground state wave function. And please note, you really haven't used your Schrodinger equation here. You've just used the fact that the lowering of the ground state will give you a null vector. All right. So I don't remember whether I did this in class when we were doing the harmonic oscillator problem. It's been a while for you guys also. If you remember, I'll be very impressed. Okay, so so what about the first excited state? Okay, so please, I will send this across to you. All right, along with my handwritten notes also, because these partly they are not too clear. But try just working it out yourselves. All right, I think it will just clarify. And when it's like exercising, right? I mean, so you exercise your brain in a particular way, it becomes much better at solving similar or recognizing certain patterns. Okay, that is what we are looking for. Yeah. So here, what is the whole situation? Here, the first excited state can be generated by putting an A plus on psi 0, right? I mean, you just do a raising operation on psi 0 and you should end up with your first excited state. So I've kept the A1 as a constant over here. And then you just do the same thing, or you just take the form of a plus, okay, which I have put up over there, and you just apply it to the wave function that you already know. All right. And by doing this, you can actually end up, I will not run through the manipulations, you will end up with this. Okay. So you will end up with this, and then you have to, of course, normalize again this A1 and figure out what you get. Okay. So that you can do. Just let me go down. Okay, I had to use some standard integrals. Nitin may have some clever way of doing it, but your ma'am, had to use some integral book to do it. Okay, I suck at integration. All right. So essentially, I think finally you end up with something which looks like this. Okay. Yeah, that's what I ended up getting. I think a A1 was just one. All right. Maybe I need not have done it. I don't know. All right. So this is essentially how you can get it. Now, what you will realize, of course, that this is an extremely painful method at getting the general solution for the wave function. Okay. So suppose I want it for the nth excited state, like, if it is like, say, the, you know, the seventh excited state, you can imagine that I have to do this crazy thing repeatedly, 7 times, right? So that's a real problem. So thereby you need to go for a general solution, which is done by solving the Schrodinger equation. Okay. So please note that the method is extremely simple and nice in certain ways, but when you want, as you like over here, you want the general solution for the nth excited state, you don't want to specify n. Okay, then you have no option but to go and solve the Schrodinger equation. Okay. So this is also something that we probably did in class. Okay, so this is the second problem that I had put up, which is the expectation value of the potential energy in the nth state of the harmonic oscillator. Now, I'm just speaking from my experience of your seniors. Okay, so not just your immediate seniors, all the people who have done this particular course with me. Somehow people are extremely uncomfortable, all right, with the idea of using the what do you call, the operator method. But believe me, for most purposes the operator method works very well. It is extremely simple. Okay, and it saves you a lot of problem. All you have to remember is how a plus and a minus operate. That's why I'm begging you to remember those things. Okay, so once you remember it, believe me, it will work out very well. All right. So in this, of course, what you have to do is remember what is your potential energy. And if you remember, it is nothing but half omega square x square, right? If I'm not mistaken. Yeah, half omega square x square. So what you have to do is to just find the potential energy in the nth state of the harmonic oscillator. Now this, of course, I just put it up as an exercise. Very, very simply thinking, uh, you know, harmonic oscillator, whether classical, whether quantum. What does it do? It essentially partitions out the expectation value of the potential energy and the kinetic energy into two equal buckets, so to speak, right? So the expectation value of the kinetic energy is equal to the expectation value of the potential energy, no matter which state you're in. You know the total energy, right? So that is n plus half h cross omega, and thereby the expectation value of the potential energy is going to be half of that. Expectation value of the kinetic energy is also going to be half of that. Okay, so you can just do this exercise to convince yourself that that is indeed what you're getting. All right, again, why do it if you know the answer? The thing is to just practice, right? So basically your brain gets used to recognizing all these patterns, and you may see it in an unusual setting, you'll still be able to recognize it. Okay, so that is the requirement that we have of basically of problem solving, because believe me, nobody is going to give these exact problems. They're going to give it in slightly different connotations, right? And you need to be able to recognize what is required and come up with the answer, and fast. All right. So now this is what yeah one has done. Essentially come up with this. You can see this is your expectation, half m omega square x square expectation value. Of course, this half m omega square is just a constant. We need not worry about it. So this is the key guy that we need to find out. So write it down in terms of your, what do you call it? Um, uh, the ladder operators. And you get finally an expression which looks like this, right? And what you have to remember over here very easily is that when you're trying to find out the expectation value, if you end up raising twice or if you end up lowering twice, then you will invariably get a zero for the inner product. Okay, so it will not work, right? Because you will be raising this to psi n plus 1 and then psi n plus 2. And then when you try and take an inner product with just psi n, you're going to get a zero because all the states are orthogonal to each other. I didn't specifically say that. I hope you remember it. Okay. Now let us go on to, so essentially you're left with the job of just figuring out what is this and what is this. And this you can do very peacefully just using the ladder operators. Please feel free to use the bracket notation. I don't know why I use these integral notation. They're very irritating. Use the bracket notation and it will be just, so I think I lost the connectivity for a bit. I'm really sorry about that. I don't know. I just suddenly found that I was talking to myself. Okay. I'm sorry about that. All right. So where were we? We were somewhere here. Yeah. Right. Yeah. So you guys are all still with me. Good. Yeah. So then, yeah, you basically find that out. And as I told you, this is trivial kind of a situation almost, but it feels nice that it is linked up with what your understanding of the whole situation is. And as you can see, you end up with n plus half h cross omega, which is the total energy of the system. Just half of that is supposed to be the potential energy. And this is the situation in any excited state of the system. All right. Okay, so now what we will do, I think, yeah, these were two problems which I wanted to solve. So I will just show you the whole set of problems that we have. Okay, okay, 1 second. I think I have done a mistake. I'll just stop share. Yeah, I have to share again. I keep forgetting this. And as usual, I can't see it. Okay, no, I can see it. Yeah. So these are the problems that we are going to look at. Can everybody see this PDF file? Is it visible, please? Okay, thank you, Medha. So what you will see is that the first one we already kind of looked through in my notes, okay, as we did for the second one, all right? So of course you can try experimenting, or rather trying to solve for the kinetic energy, and you will get pretty much the same thing. Kinetic energy, of course, you'll do P square by 2m. So you'll have to get the form of P in A plus and A minus. Now look at the third problem, please. It essentially asks you to find out the expectation value of x square, of p square, okay, for the ground and the excited state. And then it asks you to check for the uncertainty in these states. So when it asks you to check for the uncertainty, what does it mean? You actually need to get to the uncertainty in x and px, both in the ground and the excited state, and ensure that the product of the uncertainty is greater than h cross by 2, right? And it asks you to extend the answer for the nth stationary state. Okay, so kindly do that. Okay, I'm going to give this to you as an assignment. I'm not going to be doing it because we have done in class the whole thing for the infinitely deep well. All right, and here I think your life is a bit simpler because you're going to use the ladder operator method. All right. Okay, now what about the next problem? Again, please note this is a problem where you're starting off at a particular state. Okay, now please note that it's not an even distribution. Okay, it's not an even distribution. You have a mixed state which has weightage of 3 on the ground state and a weightage of 4 on the first excited state. All right, and of course there is a normalization factor. All right, so try finding A. And I think in your mind by now, you will have a quick way of getting to the normalization factor, okay? Squaring, adding, and taking the under root, okay? So this should be working out quite well, all right? And then, of course, you're supposed to construct psi xt and the mod square of that, okay? The probability square. I think again, that shouldn't be a problem. You have to find the expectation value of x and p in this particular state. Okay, what it wants you to do is to find the expectation value of P without using Ehrenfest theorem, and then prove that Ehrenfest theorem holds for this wave function. I think I'll not be too strict. I know it will hold. So go ahead and do it using Ehrenfest theorem. Okay. Now, when one is measured the energy of this particle, what values will one get and with what probability? This is pretty much a repetition of what we did in the infinitely deep well. Just do it here. So I think again, 4 is going to be something which is fairly, you should be able to do, right? It shouldn't be a problem. All right, now let us go ahead and look at the fifth problem, all right? And the fifth problem, what does it say? That the particle is in the ground state of the harmonic oscillator with classical frequency omega. When the spring constant quadruples without initially changing the wave function. Okay, so now what is happening is that your spring constant is becoming 4 times, right? So let's just have a look at how this problem will be solved. I will again leave you to solve this problem, but let's just have a small discussion on it. Okay, so I will stop the share and I will share my iScribe. Okay, and what we have over here, let me just draw this line. Okay, so you initially had a k, all right, and you had an omega which was essentially root of m by, is this correct? No, k by m, right? What is wrong with me? Root of k by m, correct? Yeah. Now what is happening is that this k is going to some k prime which is equal to 4 times k. So your omega prime is going to be nothing but root of k prime by m, correct? Which is going to be essentially root of 4k by m, correct? So which is essentially going to be 2 root of k by m. So which is going to be essentially 2 times omega. So your new omega prime now is essentially going to be 2 times the earlier omega. All right. Now, you are sitting in the ground state of the system where the fundamental frequency is omega, correct? And you will now have gone to the new system where it is essentially 2 omega. So now what are you supposed to do? You are supposed to expand the ground state of the earlier system in terms of the eigenstates of the new system. All right. So this is what you're supposed to do. All right. And please note your eigenstates of the new system, of course, they are going to have the omega prime, which is essentially delivering it. Now, do you need to do the whole thing? No. The problem actually is, I think, quite specific. So I'm going to stop it here. Let's get back to the problem. Yeah. Okay, so what it is asking is that what is the probability that a measurement of energy would still return the value h cross omega by 2? Now remember, h cross omega by 2, okay, was the ground state energy of the original system. All right. Now what is going to be the ground state of the new system? H cross 2 omega by 2. So it will become h cross omega, correct? Obviously, that is going to be the ground state. You will not be able to measure. See, any energy you measure now has to be the eigenstate of the new system, correct? So the eigenstates of the new system, the energy start off with h cross omega, right? So thereby there is almost no, not almost no chance, there is no chance. You will get zero probability Then it asks you what is the probability of getting H cross omega. So you know how to calculate this. You have to essentially figure out what is the Cn, okay, of the ground state, right? When you expand the original ground state in terms of the linear, and you know how to do that, okay? So I will leave you to try and do the fifth problem also by yourself. What about the sixth problem? All right. So this is now a calculation of the matrix elements of x square and p square. Okay. And I think if you write down, I haven't solved this particular problem myself. All right. But I think if you write down x square and p square in terms of the a plus and a minus, this should be again something that is easily done. Just remember that you have n and m, you have the kets which are there, m being the mth excited state, and n being the nth excited state. So I think you should be able to work out what are the matrix elements. Okay. Fine. One clue over here in the sixth problem. Remember, x square is linked to the potential energy. P square is linked to the kinetic energy. So you will expect these matrices to be diagonal, right? And the diagonal element should be the eigenvalues, energy eigenvalues, which you would measure for kinetic energy or for potential energy. So I think that should be a substantial clue. You can try it both ways, okay, and see whether it matches up with what you are expecting, right? I mean, I think that's partially the reason why I didn't actually take pen and paper and solve the whole thing. Okay, so let us look at the next one. It's an MCQ, all right? So what it asks is essentially the degeneracy of the first excited state of an isotropic three-dimensional harmonic oscillator is, okay? And then it gives you certain numbers, okay? So 1, 2, 3, and 6. So let me see, I will just stop the share and let me see whether I have a written solution. Again, it doesn't show. So I will stop this. All right. Just give me a minute. Okay. Okay, so I'm hoping, since it has been written in pen, but it's not been, of course, done very well. So you have been asked essentially that you have a three-dimensional isotropic three-dimensional oscillator, right? So now, so a three-dimensional oscillator, okay, by rights should have a, what do you call it, a potential energy. So should be three-dimensional in all three directions, right? So it is half k1x square plus half k2y square plus half k3z square, or you could write kx square, ky y square, kz z square. Okay, doesn't matter. When it is isotropic, of course, you can use the variable separable technique, and what will you get? You'll end up getting three one-dimensional Schrodinger equations, okay? And the form of the Schrodinger equation, of course, will be of that of the linear one-dimensional harmonic oscillator. Okay, so here you have, don't worry, I will send you over the solutions along with the problem set. I will send you over the solutions, okay, once we are done with it. All right, so just look at it. This is your one dimensional. So I think this is again something you have done in your first semester, okay? In unit 2 you have, actually there was an extension to three-dimensional problems, and this hopefully has been addressed. So essentially what you do is you write down the solution of the Schrodinger equation in the variable separable form. You have a solution which depends only on x, multiplying a solution that depends only on y, multiplying a solution that depends only on z. Once you do that, you essentially can get into a very, your parameters, the differential equation separates out into three parts, And you will realize that there is a part dependent only on x, plus a part dependent only on y, plus a part dependent only on z, and you find that is equal to a constant. And you know that cannot be really possible unless each of these parts individually are equal to a constant. So that's how you end up getting essentially three one-dimensional Schrodinger equations. So this is what you have over here. Okay. So you can see that this is just looking like a one-dimensional Schrodinger equation. You have an Ex over here. This Ex, of course, and what you get for the Y part and the Z part, you'll get an Ey and an Ez, and the three of them together will give you the total energy. Now, this is the thing that you really need to remember, that your energy depends upon three quantum numbers, nx, ny, and z. And so you'll have nx plus half h cross omega 1 plus ny plus half h cross omega 2 plus nz plus half h cross omega 3. Now remember, this is the general case. However, in this particular case, you have been told that your harmonic oscillator is isotropic. So the key word over here is the isotropy. And if it is isotropy, remember, essentially this is what happens. Your K1 will be equal to K2 will be equal to K3 will be equal to K, right? And thereby your omega 1, your omega 2 and your omega 3 will also be the same. So thereby now your answer, okay, will be your En will be n, it will be essentially n plus 3 by 2 h cross omega, okay, where n is nothing but nx plus ny plus nz. And remember, nx, ny, nz can each take values 0, 1, 2, 3 and so on and so forth. Okay, they cannot really take they basically, it's a solution of the one-dimensional harmonic oscillator, right? So what you have been asked is what is the, okay, so ground state will be unique because nx, ny, and z will all take only 0 value. All right, so now let's just stop the share because I seem to have suddenly stopped the, I know we are running out of time. Okay, so let me just go back to that. Oh man, what is this? I can't find that file again. Just a second, guys. Okay, we'll just wrap it up in 2 minutes or less. Okay. Yeah. Let me just get to the problem. Yeah. Yeah. So just let's have a look at what is the question that has been asked. The question is first excited state. Okay. Now, first excited state will be, so remember the ground state is nx, ny, nz all 0, 0, 0. First excited state will be with, possible with, you could have your nx equal to 1 or your ny equal to 1 or your nz equal to 1. All right, so essentially that should be able to give you, so let me just do this last thing. I'm going to change the page here and for myself here. So essentially your E, okay, nx, ny, nz is equal to n plus 3 by 2 h cross omega. Your n is of course equal to nx plus ny plus nz. So ground state is when nx, ny, nz are all 0, 0, 0. You cannot get lower than that. And then the first excited state could be this, or it could be this, or it could be this. Okay. So essentially there are three different quantum numbers, a combination of quantum numbers, which could essentially give you the same energy. So the degeneracy of that state becomes 3. So that's the answer. Okay. All right. I will stop here. I will send over the assignment. Okay. I'm afraid this week I will not be able to look at your assignments at all, neither the previous ones that you sent nor the current ones, because I'm just running like a crazy thing trying to get your first semester, your juniors, their first semester portions done because we have a deadline of 7 June. Okay. So I have to wrap it up. I have taken a crazy number of classes, so I don't think I'll be able to handle looking at your assignment. So you take your time, and hopefully by next week send it in to me. Okay, so that'll be good. All right, so I will send it. I will upload it again on the drive. If you have any issues accessing anything on the drive, kindly let me know. All right. Okay then. So I think we will wrap it up today, and yeah. So